The first characteristic of sound that we're going to talk about is loudness. Now, loudness is related to the intensity of a sound wave. So we're looking at the amplitude of the wave. Now, remember that intensity is calculated as power divided by area, and power is just energy per unit time. So intensity is a measure of how quickly energy is passing you. The intensity of a sound wave is a measure of the energy in the sound that is passing by in a given amount of time. Now, the human ear can detect sounds as low as 10 to the minus 12 watts per square meter. This is something we call the threshold of hearing. If the intensity is anything lower than that, it gets to be very hard to hear. Now, this is an average number. Some people can hear intensity slightly less than this. Some can't even hear 10 to the minus 12. But on average, this is about the intensity of sound waves that the human ear can hear, the lowest intensity. Now, there's no real limit to how loud a sound can be for us to hear. However, we usually don't recommend going anywhere above an intensity of 1 watt per square meter. That's known as the threshold of pain. That's where you're going to start getting irreversible damage to your ears. In fact, anytime you spend a large amount of time at high intensities in this region up here, if you spend a lot of time there, it can cause damage. But once you start reaching intensities close to 1, you're going to produce damage without proper ear protection. Perceived loudness, however, is not proportional to the intensity. For example, if you double the intensity, you're not going to double the volume, our perceived loudness. Perceived loudness is what we call volume of sound. So, what is volume proportional to? Well, it turns out that the loudness, or the volume of sound, is more closely related to a logarithmic function of the intensity. And this is where we start getting sound levels. The sound level is measured in decibels. The bell is named after Alexander Graham Bell, and yes, it is spelled correctly, B-E-L. Alexander Graham Bell, B-E-L-L, is famous for having invented the telephone. And he did a lot of work with sound levels as well. And so the unit of bell for sound level is named after him. But instead of just using the bell, which would just be this function right here, logarithm of the intensity of sound divided by some reference intensity, we multiply it by 10 to give us the decibel, or decibels. Okay, so sound level is calculated as 10 times the logarithm of the intensity of the sound divided by this reference number, I naught, which is generally taken to be the threshold of hearing, 10 to the minus 12 watts per square meter. Okay, now here's why the sound level and the intensity are quite different. If you increase the sound level by 3 decibels, that's the same as doubling the intensity. So if you have an intensity of 4 times 10 to the minus 5th watts per square meter and double that to 8 times 10 to the minus 5th watts per square meter, you've doubled the intensity, but our ear only registers an increase in 3 decibels. Now, a couple other notes here. In open areas, when you don't have walls or things that will cause echoes, the intensity of sound will diminish as proportional to 1 over r squared. Because remember, intensity is equal to power over area, and the area of the sphere is 4 pi r squared. So the intensity is proportional to 1 over r squared. However, if you're inside of a building or in any enclosed space, it becomes more complicated because then you have reflections and echoes, and all sorts of other things that you do have to deal with. And so so you can't really use this relationship, the fact that it drops off at 1 over r squared, that doesn't really work indoors. Now, just a quick note on how we actually perceive sound. When you have a sound wave come into your ear, first it goes through the ear canal and then hits the eardrum. And then that wave, since it's an oscillation or compression of air, that compression of air is going to cause the eardrum to actually vibrate. That right there, from the outer, from the earlobes through the ear canal to the eardrum, that's known as the outer ear. Now, the middle ear is this series of bones right there. The hammer, the anvil, and the stirrup. They're bones inside of the ear that oscillate due to, that move around because of the oscillation of the eardrum. And they help to transfer the vibrations from the outer ear to the inner ear. And in the inner ear, you have the cochlea, which is what is used to transform the vibrational energy from the eardrum and the hammer, anvil, and stirrup. It transfers it to electrical signals. The electrical signal then goes through the nerves up to the brain. Now, everything we've said here, let me go back here. Everything we've said here is ideal. These sounds are ideal, meaning the average person, the threshold of hearing is 10 to the minus 12. The average threshold of pain is 1. But that varies from person to person, but it also varies on the frequency of sound. So the threshold of hearing is changed. We'll just look at that one. Here's the threshold of hearing. This is the bottom line. Around normal audible tones, which would be here in this region, audible tones, the threshold of hearing is 10 to the minus 12 watts per square meter. But if you have a really low pitched sound, the intensity has to be a lot higher in order for us to hear it. So the threshold of hearing moves up to 40, 50, 60 decibels. If it's anything below that, you won't be able to hear those really low tones. Whereas if you go higher tones, like frequencies around 5,000 hertz, then the intensity can be even less than 10 to the minus 12th in order to hear it. So here you've got an intensity of, I don't know, maybe that's 10 to the minus 11th, 5 times 10 to the minus 11th, something like that. It's less than 10 to the minus 12th. Bottom line is that our perception of sound not only depends on the intensity, but it also depends on the frequency.